Hello everyone, here in this section we have double integrals in polar form. We have region R, and R is between G1 theta and G2 theta. Theta, it is between alpha and beta. So here is what we have for theta alpha, and here is beta. It is contained in a fan-shaped region. So R is between 0, A. So here is R. Or on this port we have R. So R is from 0 to this point we have A, and theta is between alpha to beta, where beta minus alpha is between 0 to pi. Now here we have part of this polar form. So here we have, in this part we have large sector, and here starting from this point, so in this part it is a smaller sector based on what we have here. So this is what I have exactly on this part. The observation that delta A is equal to area of large sector minus area of small sector, which is this part. So that part is delta A. Let's do the formula delta A equal to R times delta R times delta theta. So here is delta R, here is delta theta, and now the same for this part. Here is delta R, and here is delta theta. Find limits of integration in polar coordinates. So here we have to find the theta limits of integration, find the smallest and largest theta values that bound region R. These are the theta limits of integration. So here we have double integral over R of f of r theta dA that is equal to, so here on this part we have this example, and we have double integral. Theta is between pi over 4 and pi over 2, and r is between the square root of 2 cosecant theta and 2. This is for f of r theta, and here we have r dr d theta. So this is our function, and this is our r, or is from square root of 2 cosecant, and here is 2. And our theta is between pi over 4 and pi over 2. Example, change the Cartesian integral into an equivalent polar integral, then evaluate the polar integral. Here we have double integral of 11 over 1 plus the square root of x squared plus y squared dy dx. So here y is from negative square root of 1 minus x squared to 0, and here x is from negative 1 to 0. To change the Cartesian integral into a polar integral, substitute x equal to r cosine theta and y equal to r sine theta. Replace the x dy by r dr d theta. And determine limits for integral in polar coordinates. So here we have double integral over r. So r is our region of f of xy dx dy. This is equal to double integral over g of f of, so instead of x now using r cosine theta, and instead of y we have r sine theta, and here replacing the x dy with r dr d theta. So here on this part, what is given f of x, y, it is 11 over 1 plus the square root of x squared plus y squared. And this is equal to double integral over r of 11 over 1 plus square root of. So here instead of x, we have r cosine theta. Instead of y, we have r sine theta. So here is r squared cosine squared plus r squared sine squared. Now here on this part, factor r squared. So here we have double integral over r of 11 over 1 plus square root of r squared times cosine squared plus sine squared dx dy. And here cosine squared plus sine squared is equal to 1, and square root of r squared it is equal to r. So here is double integral over r of 11 over 1 plus r dx dy. Now replace double integral over r 11 over 1 plus r dx dy with double integral over g of 11r over 1 plus r dr d theta. Now sketch the region of integration to determine the limits of integration. So here is what we have for y equal to negative square root of 1 minus x squared, and here is our r, here is theta. So find the r limits of integration. So rays starting at origin, here is origin, and cutting to the region in the direction of increasing r. The r limits of integration are values over the ray enters and leaves region. So the r value may be a function of theta. The rays enter the region of integration at r equal to 0. So r equal to 0 to r equal to 1. So r is between 0 and 1. Because the rays leave the region of integration at r equal to 1. Then find theta limits of integration. The theta limits are the smallest and largest values of theta that bound the region of integration. The lower limit of for theta it is equal to pi. Because here we have first quadrant, second quadrant, and here is third one. And this is where we started, and that is this is theta equal to pi, and here is where it's ending, and that is theta equal to 3 pi over 2. So theta is between pi and 3 pi over 2. So the limits of integration are between 0 and 1 inclusive, and theta between pi and 3 pi over 2 inclusive. So first integrate with respect to r. Here we have integral from pi to 3 pi over 2 of 11 times r minus natural log of r plus 1. This is from 0 to 1 d theta. So evaluate the result over limits of r. So here using r equal to 1, we have 11 times 1 minus natural log 1 plus 1. So here is 11 times 1 minus natural log 2. Then using 0, we have 11 times 0 minus natural log 1. So natural log 1 it is 0. So here on this part we have 0. Now integrate with respect to theta. Here we have 11 times 1 minus ln 2 times theta. This is from pi to 3 pi over 2. And this is equal to 1 minus ln 2 times 11 pi over 2. So this is our final answer for double integral. Note that here what I did, again, I used 3 pi over 2 instead of theta, and used pi instead of theta. So first using 3 pi over 2 here, and then minus using pi here for theta. Or we can subtract these, 3 pi over 2 minus pi, that is pi over 2, and then use that here. We're going to have same result. Area in polar coordinates. The area of closed and bounded region R in the polar coordinate plane is A equal to double integral over r dr d theta. Example, find area of region cut from the fourth quadrant by the cardioid r equal to 1 minus cosine theta. Based on what is given, here we have the integral. Theta is from 3 pi over 2 to 2 pi because of this fourth quadrant, and r is between 0 and 1 minus cosine theta based on what is given. r dr d theta. So this is equal to, first integrate with respect to r. So here we have integral from 3 pi over 2 to 2 pi. Integrate, here we have r squared over 2. This is from 0 to 1 minus cosine theta d theta. So here instead of r, use 1 minus cosine theta. We have integral 3 pi over 2 to 2 pi of 1 minus cosine theta squared divided by 2 d theta. And this is equal to integral 3 pi over 2 to 2 pi of, so here we had second power, and this part, it is equal to 1 minus 2 cosine theta plus cosine squared theta divided by 2 d theta. Now integrate by using half and formula, which is what they have here, cosine squared theta is equal to 1 plus cosine 2 theta divided by 2, and factoring of a constant. Then integrate. So this is equal to integral 3 pi over 2 to 2 pi of 1 over 2 minus 2 cosine theta over 2 plus cosine squared theta divided by 2 d theta. Now here on the spot I used half angle formula, cosine square, it is equal to 1 plus cosine 2 theta over 2. So I used instead of what we have here on this part, and then divided by 2, so denominator here we have 4. And then I try to have same denominator for all of these, so multiply by 2 on this part, and multiply by 2 here. So here we have 1 over 4 minus 4 cosine theta over 4 plus 1 over 4 plus cosine 2 theta over 4. Factor of 1/4 and then integrate with respect to theta. So this is equal to 1/4 times 3 theta minus 4 sine theta plus sine 2 theta over 2. This is from 3 pi over 2 to 2 pi. So here I use theta equal to 2 pi on the first part here, and then subtracted. And here I use theta equal to 3 pi over 2. So this is equal to 1/4, 6 pi minus sine 2 pi is 0, and sine 4 pi is 0, so here we have 0. So on the first part here we have 6 pi minus, on the second part here is 9 pi over 2 minus 4 times sine 3 pi over 2, it is equal to -1, so we have -4 times -1, it is positive 4, and sine 3 pi it is 0. And so this is equal to 3 pi over 8 minus 1, so simplify, this is our final answer.